Hello everyone, my name is Moudden and I'm a PhD student from the ISI laboratory at the National School of Applied Sciences of Tetouan at Malik Saadi University. Under the supervisor of Professor Otman Aghzout, it is my pleasure to be here today to discuss my research intituled Radiation Pattern Stability and Miniaturization Improvement of Planar Antennas for Radar and Medical Imaging using the theory of characteristic modes. I would like to thank my supervisor and co-authors for the collaboration in this work and the organizers and the reviewer who have made this conference possible. Now we will move to see the content that will follow in this presentation. Firstly, we have a brief introduction, then we'll conduct a model analysis of planar structures that include circular structures and equivalence of magnetic and electric modes. And finally, we have a conclusions. Now I want to explain about introduction. The microwave antennas are essential components in a variety of applications, including radar system and medical imaging for the diagnosis and treatment of the various diseases and injuries. The use of antennas in medical imaging has opened up new avenues for high resolution, no invasive imaging that can help diagnose and monitor various medical conditions. However, as the demand of high performance of this application has increased, there is need for miniaturization techniques that maintain the stability radiation pattern of planar antennas. On the other side, the theory of characteristic mode has emerged as a powerful tool for optimization performance of antennas. By using this theory, it's based in the idea that the field of an antenna can be represented as a superposition of different modes, each one with its own characteristic properties. It is originally developed by Garbach and refined by Moudden and Harrington. It is my great pleasure to have Professor Marta Cabedo-Fabrés as a co-advisor for my thesis. She is one of the professors that they apply this theory in the field and microwave and planar structures. Therefore, to design analysis and protect the model antenna performance before fabrication, we use the 3D commercial electromagnetic simulators such as FECO, CST, or HFSS. The theory of characteristic mode offers several advantages over the other numeric methods commonly used in the antenna design, such as comprehensive analysis, mode decomposition, design optimization, faster design process, and design flexibility and accuracy. Now we move to explain the work proposed in this paper. Firstly, we have a model analysis of planar structures. The first study consists of the circular plates with different radius. These plates were analyzed using the theory of characteristic mode method to compare the resonant behavior. The frequency variation of the model significance for the first resonant mode of the circular plates with different radius are shown in figure 3. As we can observe, the first circular plate with a radius of 5.5 mm has 3 degenerated resonant mode, while the second circular with radius of 11 mm has 5 degenerated resonance mode, and the circular plate with radius of 22 mm has 10 degenerated resonance modes. As a conclusion, with the radius of the circular increases, the first resonant mode G1, G2 shifts toward low frequencies. New mode also appears as amount of metal increases. Finally, the model significance property is sufficient to specify all the modes and clarify which of them is responsible of the resonant effect. The 3D radiation pattern associated with the first mode G1 for the circular plates of different radius vary with electrical length of each structure showing variation degree of each mode G1. The 2D degenerated radiation pattern of the vertical plane generated by the first mode of the circular plates are identical with different phase rotation. According to many research papers, the circular loops showing a high stability directional radiation pattern compared to the other structures and proved a new structure of merit of characteristic mode, which can certainly help in the antenna design process. For this reason, we propose the kind of structures in our second study. It consists of the circular loops with different widths. These loops were analyzed using the characteristic mode method to compare the resonance behavior. The variation with the frequency of the middle significance for the first resonance mode of the circular loops with different radius is shown in figure uh, 7. It is extracted from all cases that the symmetry modes G1, G2 exhibit resonance frequency in all the loops with the shifting to low frequencies. The resonance of the mode G1 depends on the radius of the loop, which is the sum in all cases. In construct, the resonance frequency modes of the G3, G4, G5, and G6 change a lot from one case of to the other. Table 2 summarizes the results associated with the first mode of the study structures according to the plot of the model significance. The results show that the first mode, G1 of the circular loop with the width equals to 8.5 mm and 6 mm, are broadband radiator with associated radiation bandwidth bigger than 100%. The circular loops with width of 3.5 and 1 mm are broadband radiator with an associated radiation bandwidth, and the model quality factor gets bigger than width of the loops increases. However, the results show that when the width of this circle increases, it increases the half-power bandwidth and the angle of the main loop value increases. The 3D radiation associated with the first resonance mode G1 for the circular loops of different widths 6 and 3 and 1 mm, consisting for more radiation field in all directions that the circular loop with 8.5 mm show noticeable degree of variation. The 2D radiation pattern of the vertical plane generated by the first mode of the circular loops are identical with different phase rotation and are present an omnidirectional characteristic behavior. The final study is focused on the technique adopted to reduce the size of the circular plates through obtaining the equivalence future demonstration between the magnetic and electric modes. The circular plate with a radius of 11 mm has two miniaturization design at the 16 GHz. The first equivalent geometry is the circular loop 1 with width is 4.1 mm and external radius 6 mm. The second equivalence geometry is the circular loop 2 with the width of 2 mm and an external radius of 10.5 mm, yielding the 46% size reduction, as shown on the left side. The variation with the frequency of the model significance for associated with the mode resonance at the 16 gigahertz of different structures are shown in the right side. Table 3 provide for information of the model significance for the structures of figure 9 regarding the resonance frequency, radiation bandwidth, and half-power bandwidth associated with the SAM modes at the 16 GHz. The first mode of the circular plates and the circular loops one is broadband radiator with associated radiation bandwidth bigger than 100%. It can also be seen that the circular loops 2 represent with radiation bandwidth than circular plate cases. It is also found that the circular loop 1 show whether half power bandwidth equals 136.11 degree, where the circular loops 2 show half power bandwidth equals 47.2 degree at the radiation pattern of the vertical plates. Conclusions. Planar antennas performance has been analyzed of microwave imaging, in particularly for early cancer tumor detection and radar application. Present technique offer a reduction in the size 46% and stabilization pattern, and the geometrical parameter as employed to improve the bandwidth widths and half power bandwidth are and the resonance frequency of each characteristic modes. Thank you for your attention.